What does it mean for a star to die? Not in the gentle fading of old age, nor in the glorious self-immolating blast of a supernova that seeds the cosmos with new life. No, this is something else entirely, something more primal. Imagine a death that is not an end but a complete and total unravelling. A dissolution of identity where every atom that once formed a brilliant burning sun is stretched, shredded and consumed by a darkness so absolute it defies the very laws of light. For centuries this was a nightmare confined to the chalkboards of theorists, a mathematical horror story whispered in the quiet halls of astronomy. An event of such unimaginable violence, we could only ever paint it with the broad strokes of imagination and the cold, sterile language of physics. We called it a tidal disruption event, a name that feels almost clinical, antiseptically clean for the cosmic butchery it actually describes. But we are now living in a new age of discovery. We have built eyes capable of peering across unimaginable gulfs of space-time eyes that can resolve the impossibly faint echoes of creation and destruction. And for the first time, we have pointed these new eyes at the precise moment a star met its doom. What we are about to show you is not just an artist's impression, not a mere simulation. It is a reconstruction, a digital ghost built from an avalanche of real-world data, rendered in a clarity so profound, it feels as though you could reach out and touch the very fabric of this celestial execution. This is the story of that star. This is its final, terrible and breathtakingly beautiful scream. Before its fateful plunge, the star was an unremarkable thing of beauty, a placid sphere of hydrogen and helium like countless trillions of others humming across the universe. For nearly 10 billion years it had traced a calm, predictable path through the star fields of its home galaxy, a stately dance partner in the immense gravitational ballet of its local cluster. Its life was one of serene nuclear fire, a constant steady fusion reaction in its core that pushed back against the crushing weight of its own gravity. It had perhaps warmed planets that we will never know its light-bathing worlds in a life-giving glow for geological ages. It was a sun, a bastion of stability and light in the infinite cold. But in the cosmos, nothing is permanent. No orbit is truly safe forever. A slight, almost imperceptible gravitational nudge from a passing stellar neighbour, a cosmic fender bender billions of years in the making, was all it took to alter its destiny. Its ancient stable orbit was perturbed, its path subtly but irrevocably bent. It was cast out of its familiar celestial neighbourhood and sent on a new terrifying trajectory, a long, slow, accelerating fall toward the galactic centre, toward the silent monarch that reigns there, toward the supermassive black hole. You must understand what this entity truly is. It is not a hole in the conventional sense, not an empty void. It is the opposite. It is an impossible concentration of substance, a place where millions or even billions of suns have been crushed down into a single point of zero volume and infinite density, a singularity. It is a rip in the fabric of space-time itself, an object so gravitationally dominant that it dictates the motion of every star, every cloud of gas, every speck of dust for hundreds of thousands of light years in every direction. It is the gravitational anchor around which its entire galaxy spins. It is silent. It is invisible. Its presence is betrayed only by the frantic, dizzying orbits of the stars closest to its stars that whip around the unseen behemoth, like planets around a sun but at speeds of millions of miles per hour. And surrounding this point of impossibility is a boundary, a perimeter of no return known as the event horizon. This is not the physical surface you could touch. It is a mathematical line in the sand of space-time. It is the precise distance from the singularity, where the gravitational pull becomes so immense that the escape velocity exceeds the speed of light. Anything that crosses this threshold, a stray asteroid, a cloud of interstellar gas, a wandering star, is lost to our universe forever. Its information, its history, its very existence is erased. The event horizon is a cosmic waterfall, and light itself cannot swim upstream. As our condemned star accelerated on its new path, it began its final desperate dance with this gravitational titan. From a distance, the journey seemed almost graceful, a long, sweeping arc that brought it closer and closer to the galactic core's dark heart. The light from its stellar neighbours would have bent and warped around the immense gravitational lens of the black hole, creating distorted, ghostly images of the galaxy beyond. The star itself, however, was still whole, its own gravity keeping it tightly bound together. It was a cohesive sphere of plasma, a fortress of fusion. But it was now entering a region of space where the laws of physics are pushed to their absolute breaking point. It was approaching a line of cosmic demarcation, an invisible boundary of destruction known as the Roche limit. This is not the event horizon itself, but a much wider perimeter, a kill zone defined by the brutal physics of tides. Here on Earth, the moon's gravity pulls on our oceans, creating the familiar ebb and flow of the tide. It does this because the side of Earth closer to the moon is pulled slightly more strongly than the side farther away. Now amplify that effect by a factor of 1 billion. Imagine a gravitational force so steep, so intensely focused, that the difference in pull from one side of an object to the other is not a gentle tug, but a cataclysmic, irresistible shearing force. This is the weapon the black hole wields. As the star crossed the Roche limit, this tidal force began its monstrous work. The side of the star facing the black hole was being pulled with exponentially greater force than the trailing side. The star, once a perfect sphere, began to warp. It elongated, stretching out into a colossal egg shape, its fiery plasma groaning under the impossible strain. You are witnessing the moment a star loses its structural integrity. The delicate balance it had maintained for 10 billion years between its own internal gravity and the outward pressure of its nuclear core was shattered. The black hole's gravity was no longer pulling on the star as a single object. It was now pulling on each individual part of the star differently. It was dismantling it atom by atom from the outside in. The outer layers of stellar gas, the star's atmosphere, were the first to be stripped away. They were siphoned off, peeling away from the main body like fiery ribbons torn from a flag in a hurricane. These tendrils of plasma, superheated to millions of degrees, began to form a luminous tail trailing behind the deformed star, a prelude to the main event. The star was bleeding its substance into the void, a sight of both terrible beauty and profound cosmic violence. What followed was not an explosion, but a dismemberment. The process known clinically as spaghettification is a far more intimate and gruesome end. With the tidal forces now completely overwhelming the star's own gravity, the star was drawn out into a single, impossibly long, thin filament of incandescent matter. Imagine pulling a piece of taffy until it becomes a delicate thread. Now imagine that piece of taffy is 100,000 miles wide and contains the mass of a sun. The star's very shape ceased to exist. It became a river of light, a celestial noodle stretching for millions of miles, one end already disappearing into the darkness of the black hole, while the other was still being torn from the dying stellar core. The physics at play are staggering. The material in this stream was being accelerated to a significant fraction of the speed of light. As it was stretched, it was also compressed, laterally squeezed by the tidal forces into a narrow, dense current of plasma, hotter than anything the star had ever produced in its core. This stream was not silent. It was a source of the most intense radiation imaginable, a scream of matter being tortured on a gravitational rack, a scream rendered not in sound but in brilliant high-energy X-rays and gamma rays blasting out into the cosmos. This river of stellar ruin did not simply fall straight into the black hole. The laws of orbital mechanics, even in this extreme environment, still hold sway. The stream of material possessing immense angular momentum from its initial orbit could not make a direct plunge. Instead, it was whipped around the black hole, a terrifying cosmic lasso of fire. This is the moment that transforms a dark, invisible object into the brightest beacon in the night sky. The material from the dead star begins to collide with itself as it orbits, forming a swirling, chaotic, pancake-shaped structure around the black hole's equator and accretion disk. This is the black hole's dinner plate. It is a temporary, brilliant, and utterly violent structure. The friction between particles of gas in this disk, all orbiting at relativistic speeds, is unimaginable. It generates heat that makes the surface of a normal star seem frigid. Temperatures in the inner regions of this newly formed disk can soar to tens of millions of degrees. The accretion disk shines with a ferocity that can outshine the combined light of every single star in its host galaxy. For a brief period, perhaps a few months or years, the death of this one single star illuminates the entire galactic core, making the invisible black hole spectacularly, blindingly visible. You're watching a celestial autopsy. The light from this blazing accretion disk is not just a funeral pyre, it is a message. Encoded within its spectrum, within the flicker and fade of its X-ray emissions, are the secrets of the star that was. We can read its chemical composition, analysing the elements forged in its core over billions of years. We can measure the incredible magnetic fields twisted and amplified in the churning plasma of the disk, which can act as a cosmic particle accelerator, launching jets of matter away from the black hole's poles at nearly the speed of light, and most profoundly, by studying the way this matter orbits by observing the subtle warping of light and time near the event horizon. As predicted by Einstein's theories, we can probe the nature of the black hole itself. We can measure its mass with astonishing precision. We can even determine how fast it is spinning a gravitational gyroscope rotating at the heart of the galaxy. The black hole, for so long a creature of pure theory, is forced to reveal its properties. The star, in its final act of destruction, becomes a celestial flashlight illuminating the darkest object in the universe for our instruments to study. It sacrifices itself to give us a glimpse into the abyss. The event is fleeting. The cosmic blaze is temporary. Over the course of months and years, the material in the accretion disk is inexorably consumed by the black hole falling past the event horizon and vanishing from our observable universe. The river of plasma runs dry. The brilliant light of the disk begins to dim, the X-ray scream fades to a whisper and then to silence. The galactic core returns to its state of brooding darkness. The black hole, now slightly more massive than before, retreats back into invisibility. The brief violent and incandescent spectacle is over. All that remains is a faint expanding cloud of stellar material that was thrown clear during the initial disruption, the portion of the star that escaped a ghostly testament to the life that once was. For eons we could only imagine this sequence of events. We could model it with computers, sketch it on paper, but we could never truly witness it. The universe is vast, and these events are rare, perhaps only occurring once every 10,000 years in a galaxy like our own. To catch one in the act required a combination of luck, patience, and technological power that we have only just now achieved, but we did it. We were watching. And the torrent of data we collected, the petabytes of information captured by a global network of telescopes, has allowed us to build what you're seeing now. This is not just a visualization. It is a new form of cosmic cartography, a map of destruction drawn with the light of a dying star. Every photon, every X-ray, every gravitational whisper has been collected and reassembled to create this stunning, terrible vision. We have peered into the gravitational maw. We have seen the star stretch and break. We have watched the accretion disk ignite and fade. The star is gone. Its 10 billion year journey has ended in a final luminous flash. But in its death, it has given us a gift. A message written in the language of high-energy physics, a story of gravity, time, and cosmic annihilation. A message that we are finally, after all this time, ready to read. The challenge now is to decipher it, to unlock the secrets that lie hidden within this ghostly light, secrets that promise to rewrite our understanding of the most mysterious and powerful objects in the entire cosmos. And so, these gravitational anchors, these silent monarchs holding court, at the centre of every major galaxy, remain shrouded in absolute mystery. We knew they were there. Their presence was betrayed by the frantic, impossible orbits of the stars closest to them, stars whipped around an invisible focal point like planets, tethered to a sun 1,000,000 times their own. For decades, this was the extent of our knowledge as sensors of ghosts. We could weigh them, measure their sphere of influence, and map the gravitational cage they built around themselves. But we couldn't see them. They were by their very nature the embodiment of absence, a tear in the fabric of space-time so profound that not even light, the universe's swiftest messenger, could escape its pull. They were the ultimate enigma, a physical paradox of infinite density and zero volume, a place where the laws of physics as we understand them simply break. How then could we ever hope to truly understand a monster that consumes all evidence of its own existence? How do you study a predator that leaves no tracks? The answer, physicists reasoned, was not to look for the creature itself, but for the echoes of its ferocity. You don't try to photograph the hurricane, you document the wreckage it leaves in its wake. And in the cosmic ocean there could be no greater spectacle, no more profound act of destruction than the moment one of these galactic titans finally decided to feed. This was the theoretical event that consumed the careers of astrophysicists, a cosmic ballet of such violence and grandeur it felt more like mythology than science. They gave it a name that was both deceptively simple and chillingly descriptive, a tidal disruption event, a TDE. It was a theoretical prediction, a ghost story told in the complex language of general relativity, a vision of what happens when a star, a glorious sphere of thermonuclear fire that has burned for billions of years, makes one wrong turn on its galactic journey. It was a prediction of a star being eaten alive. To even begin to comprehend such an event, you have to discard your earthbound intuition about gravity. Here on our world, gravity is a gentle, persistent force. It keeps our feet on the ground and the moon in the sky. The moon pulls on our oceans, creating the tides, and this is the crucial foundational concept. The side of the Earth closer to the moon is pulled slightly more strongly than the side farther away. The planet itself is sturdy enough to resist being deformed by this gentle difference, but our fluid oceans are not. They bulge. Now imagine amplifying that tidal force not by 1,000 times, not by 1,000,000, but by a factor of trillions upon trillions. Imagine replacing our moon with an object that contains the mass of 4 million suns, all crushed down into a space smaller than our solar system. That is the supermassive black hole at the heart of our own galaxy Sagittarius A, and its gravitational pull is not gentle, it is a weapon. As an unlucky star approaches this behemoth, it isn't pulled in uniformly like a marble rolling into a drain. Instead, the tidal difference becomes catastrophically extreme. The edge of the star closest to the black hole experiences a gravitational pull that is immensely and incomprehensibly stronger than the pull on the star's far side. This differential force, this gravitational gradient, becomes a cosmic torture device. The star, a body held together by its own immense gravity, suddenly finds itself in a tug-of-war with a god, and it is a war it cannot win. The black hole doesn't just pull the star, it stretches it. The process is a horrifyingly elegant execution of physics. The star's spherical shape begins to distort, elongating into an egg, then a teardrop pulled taut by the relentless tidal shear. The very forces that have held it in a delicate hydrostatic equilibrium for eons are systematically overwhelmed. It is a slow, methodical dismantling, a stellar autopsy performed at a distance by the universe's most powerful force. This is the origin of the term that sounds almost whimsical were it not so terrifying, spaghettification. The star is literally drawn out into a long, thin noodle of incandescent plasma. Its core, where for ages hydrogen atoms were fused into helium in a controlled life-giving fire, is torn asunder. Its outer layers are stripped away, unravelling like a ball of yarn. We are witnessing the deconstruction of a sun, the unmaking of a celestial body atom by atom. But to truly grasp the finality of this act, we must journey to the edge of the abyss itself, to a boundary that isn't made of matter or energy, but of pure geometry. A place that isn't a surface you can touch, but a threshold you can cross only once. This is the event horizon. Think of it as the universe's ultimate shoreline, the coast of a sea of infinite gravity from which no traveller can ever return. It is not a wall or a membrane, but an invisible sphere of influence defined by a simple, terrifying law at this precise distance from the black hole's central singularity. The escape velocity required to break free surpasses the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary, a stray asteroid, a cloud of gas, a beam of light, the shredded remains of a star, is lost to our observable universe forever. It is the point of no return writ large across the fabric of spacetime. Information that passes this veil is permanently erased from history. It is a one-way door. The event horizon itself is not the black hole. It is merely its shadow, the edge of the casement from which no light can emerge. Inside this shadow lies a complete mystery, a place where space and time are thought to swap roles, where all paths lead inexorably to the central singularity, a point of infinite density, where our understanding of reality ceases to have any meaning. The theoretical blueprint for a tidal disruption event therefore became a story told in two acts separated by this ultimate boundary. The first act is the spaghettification, the dramatic and violent shredding of the star that occurs outside the event horizon. This is the part of the story we could in theory witness. As the star is unspooled into a streamer of superheated gas hundreds of millions of kilometers long, it doesn't just fall straight in. Much like water circling a drain, the stellar remains are flung into a blistering chaotic orbit around the black hole. This material, once the proud body of a sun, forms what is known as an accretion disk, and this disk is where the real fireworks begin. This is the stellar feast. The friction and magnetic shear within this swirling vortex of plasma are so extreme that the gas is heated to millions of degrees Celsius. It begins to glow with an intensity that can temporarily outshine the combined light of every other star in its host galaxy. This is the cosmic scream we would be looking for, the dying cry of a star translated into light. The theoretical models predicted a very specific signature for this cataclysmic event. It wouldn't be a sudden bang like a supernova. Instead, it would be a flare that rises in brightness over several weeks or months as the stellar debris falls back towards the black hole and begins to accrete. It would shine most brightly, not in visible light, but in the higher energy wavelengths of the electromagnetic spectrum, ultraviolet, and most tellingly X-rays. The inner edge of the accretion disk churning just beyond the event horizon would be so hot that it would radiate a torrent of X-ray photons, a beacon, signalling that a celestial sacrifice was underway. After reaching its peak brilliance, the flare would then slowly and predictably fade over the course of several years, following a specific mathematical curve as the last of the star's material was consumed or flung back out into space. Some models even predicted that the formation of this new supercharged accretion disk could launch powerful jets of particles from the black hole's poles, twin blowtorches moving at nearly the speed of light piercing through the galactic center. This was the blueprint the celestial fingerprint astronomers would need to find. A rapidly brightening flare from the dead center of a quiet galaxy, a flare that shone with the heat of a million suns rich in UV and X-ray light, and then faded gracefully back into the darkness. It was a beautiful, compelling and complete theory, but for decades it remained just that, a theory, a ghost story without a ghost. And the reason for this was a simple, humbling matter of cosmic scale and probability. Our universe is a place of unfathomable size and emptiness. These stellar feasts, for all their violence, were predicted to be exceptionally rare. In a typical galaxy like our own Milky Way, a star is only likely to wander close enough to the central supermassive black hole to be tidally disrupted once every 10,000 to 100,000 years. For human astronomers with their fleeting lifespans and limited view of the sky, the chances of being alive and looking in the right direction at the right moment were infinitesimally small. It was an observational challenge of daunting proportions. You're searching for a single brief flash of light, a transient cosmic firework in a universe filled with 100 billion galaxies, each containing 100 billion stars. Most of these galaxies are hundreds of millions or even billions of light years away. By the time the light from a TDE reaches our telescopes, the event has been over for eons. We are always looking at the past. Furthermore, the centers of galaxies are notoriously crowded and dusty places. The very heart of our own Milky Way is shrouded from our view in visible light by thick clouds of interstellar gas and dust. We would be trying to spot a flickering candle through a dense cosmic fog. The signal could be easily mistaken for other more common cosmic explosions like a particular type of supernova, or confused with the random flickering of an already active galactic nucleus, where a black hole is constantly feeding on a steady diet of gas rather than a single spectacular meal. The early searches were frustrating, a testament to the difficulty of the quest. Astronomers used the first generation of X-ray telescopes orbiting high above the Earth's obscuring atmosphere to stare at the centers of massive galaxy clusters, hoping to get lucky. They sifted through mountains of archival data from optical surveys, running algorithms designed to pick out the unique light curve of a TDE from the noise of a billion other variable objects in the sky. It was like listening for a single specific whisper in a hurricane of cosmic static. For years, they found nothing definitive. There were tantalizing hints, strange flares from galactic nuclei that almost fit the profile, but they were too faint, too short-lived, or their light signature was ambiguous. The cosmic predator remained a phantom. The theoretical blueprint was perfect, the physics was sound, but the universe was stubbornly refusing to provide a clear example. The greatest show in the cosmos was playing out in empty theatres, its light fading into the void unseen. The question loomed large in the astronomical community. Would we ever be able to capture one of these elusive events? Would we ever actually witness with our own eyes the ghost in the machine finally devouring a star? To do so would require new eyes on the sky, a new generation of robotic telescopes capable of scanning the heavens with unprecedented speed and sensitivity, creating a dragnet wide enough to finally catch one of these rare, brilliant fish. The hunt was on, but the prey was proving to be the most elusive in the cosmic kingdom. We needed a breakthrough. We needed to be able to see the whole sky all the time. Because out there in the silent darkness between the galaxies, the screams of dying stars were travelling towards us, carrying a story of unimaginable power and destruction. We just had to be ready to listen. And so the theoretical stage was set. On the chalkboards of pioneers and in the sprawling equations of general relativity, a star could be sacrificed to the ultimate gravitational altar. The physics was elegant, terrifying, and internally consistent. But a prediction, no matter how compelling, is merely a ghost in the machine until its shadow is captured in the real, messy, and infinitely vast universe. Finding that shadow, that fleeting proof of cosmic annihilation, would prove to be one of the great astronomical detective stories of the modern age. It would not begin with a bang, but with a whisper. The first hints were not cinematic streams of stellar fire. They were something far more subtle, more cryptic. Imagine you are staring at a map of a city at night, a city you know to be ancient, quiet, and largely asleep. For decades, the central square has been dark. Then for one brief, inexplicable moment, a single window ignites with the fire of 1,000 suns, only to slowly, methodically fade back into the familiar darkness over months. You saw the flash, but you missed the event. You have evidence of a cataclysm, but no understanding of its cause. This was the confounding reality for astronomers in the late 20th century. The first potential clues arrived as photons of extreme violence X-rays. Space-based observatories like Germany's Rosat satellite, designed to chart the high-energy sky, began to detect these bizarre outbursts. They were cosmic transients, appearing from nowhere and then vanishing. Crucially, they were not scattered randomly across the heavens like the brilliant, well-documented deaths of massive stars in supernova explosions. Instead, these enigmatic flares seemed to have a preferred address. They blinked into existence directly in the heart of otherwise unremarkable dormant galaxies. Galaxies whose cores were thought to be silent, their central black holes slumbering. It was as if a sleeping dragon had suddenly exhaled a single searing plume of fire. These X-ray signals were the perfect calling card for a tidal disruption. As stellar material stripped from its parent star plunges towards the event horizon, it doesn't simply fall in. It is compressed and accelerated to nearly the speed of light, forming a temporary chaotic swirl of plasma known as an accretion disk. The friction within this nascent disk, this gravitational death spiral, is so immense that it heats the gas to millions of degrees, causing it to blaze with an intensity that shines brightest in high-energy X-rays. The theory predicted this very signature, a sudden brilliant X-ray flare from a galactic nucleus followed by a long, predictable decay as the stellar matter is consumed. Yet this evidence, tantalizing as it was, existed on the very edge of ambiguity. Each detection was a single blurry point of light on a digital sensor, a smudge on the cosmic canvas. It was a flare, a rise and fall in brightness, but nothing more. There was no detail, no structure, no way to resolve the image and see the elegant, terrible arc of a spaghettified star. The telescopes of the era, powerful as they were, lacked the resolving power. They could tell us where the fire was and how brightly it burned, but they could not show us the shape of the flames or what was being consumed. The celestial crime scene was reduced to a single, overexposed photograph. This lack of resolution created a profound problem of identity. Because the universe we were learning is filled with things that go bump in the night. The most common suspect for any sudden cosmic flash is a supernova. These are the titanic explosions that mark the end of life for massive stars, and they can easily outshine their entire host galaxy for weeks. So when a burst of light was seen from a distant galaxy's core, the first question was always the same. Are we witnessing a star being eaten, or are we simply seeing a conventional star exploding in an unfortunate location, its light merely overlapping with the galactic centre by chance? Distinguishing between these two violent possibilities became a forensic science. The key piece of evidence was the light curve, the plot of the event's brightness over time. A supernova's light curve has a characteristic shape. It rises to a peak brightness quickly, then fades in a complex manner, often powered by the radioactive decay of newly forged heavy elements like nickel and cobalt. A tidal disruption event, in theory, should behave differently. After the initial chaos, as the bound stellar debris falls back towards the black hole, its rate of return should follow a very specific physical law. The brightness should decay smoothly proportionally to time to the power of -5/3. This precise mathematical fingerprint, t to the -5/3, became the theoretical gold standard for identifying a TDE. But theory is a clean room, and the universe is a storm. The early data was noisy, incomplete. Telescopes couldn't stare at these fleeting events continuously. They would catch a data point here, another a week later, maybe a third a month after that. Astronomers were trying to connect the dots to reveal a perfect curve, but they had too few dots, and each one was smudged with uncertainty. A noisy, poorly sampled TDE light curve could look suspiciously like a peculiar type of supernova. A chance alignment could place a supernova so perfectly in the galactic core that it was impossible to rule it out. For every promising candidate, there was a chorus of justifiable doubt. The verdict on these first events was often inconclusive. The ghost remained a ghost. The game changed with the advent of massive automated sky surveys. Projects like the Sloan Digital Sky Survey began a new era of astronomical observation. The strategy shifted from painstakingly pointing a telescope at a single known target to systematically photographing the entire sky, night after night after night. These robotic telescopes created a dynamic map of the cosmos, a moving picture instead of a static portrait. Sophisticated software could then compare last night's image of a patch of sky with the image from the week before, searching for anything that had changed. Any new point of light that appeared where none was before was flagged as a transient. This new approach began to catch TDE candidates in the act right as they flared up. The net was cast wider than ever before, and the number of potential detections grew. Yet this deluge of new data brought with it a new, more insidious problem. The universe, it turned out, had another way to mimic a tidal disruption, a confounder so powerful it would muddy the waters for years. This was the chaotic, unpredictable nature of the active galactic nucleus, or AGN. While the TDEs we were searching for were thought to happen in quiet galaxies, many galaxies are anything but. Their central supermassive black holes are not dormant. They are feasting. They are surrounded by massive permanent accretion disks, vast whirlpools of gas and dust that have been feeding the central monster for millions of years. These AGNs are the cosmic lighthouses of the universe, blazing with a ferocious sustained light. But their brightness is not constant. It flickers. It burps. Instabilities in the accretion disk can cause it to suddenly brighten by a factor of 10 or more a flare-up that for a brief period can look uncannily like the beginning of a TDE. Trying to spot the clean single signal of one shredded star against the perpetual raging storm of an AGN is like trying to hear a single violin string snap in the middle of a volcanic eruption. The background noise is overwhelming. Many promising TDE candidates from this era, initially hailed as breakthroughs, were later re-examined and reclassified. Looking back at archived plates of the galaxy, astronomers would find that its nucleus had always been subtly variable, a telltale sign of a low luminosity AGN. The dramatic flare was not a unique death cry. It was just a particularly violent shudder from a monster that was already awake. This constant misidentification was a source of immense frustration. It forced scientists to refine their search to focus exclusively on galaxies that had demonstrated decades of perfect unwavering silence. The ideal hunting ground was a galaxy so quiescent, so utterly dormant that any flash from its core could only be the herald of a new and terrible event. Even when a candidate appeared in the perfect location, a truly quiet galactic core, and even when its light curve seemed to match the to the -5/3 decay law, the fundamental limitations of the available instruments left the deepest questions unanswered. We were still staring at a dot of light. The physics of the disruption itself, the beautiful, horrifying process of spaghettification, was entirely locked away inside that single pixel. All of our models, all of our supercomputer simulations depicted a star being stretched into a celestial noodle hundreds of times longer than our own solar system. But we had no direct observational proof of this stellar noodle. We couldn't measure its length, its temperature gradient, its velocity. The evidence was entirely circumstantial, inferred from the fading glow of the wreckage. This observational barrier meant that a host of fundamental puzzles remained unsolved. For instance, how does the accretion disk, the engine of the TD's light, actually form? The stream of shredded stellar material upon returning to the black hole must somehow collide with itself, shedding energy and angular momentum to settle into a relatively stable circular orbit. The physics of this circularization process was a black box. Did it happen through powerful shock waves as the stream intersected itself? Did magnetic fields play a dominant role, weaving the gas into a coherent flow? The early low-resolution data was completely blind to this critical formative stage. We were only seeing the aftermath, the glowing embers, not the ignition of the fire, and then there was the mystery of the jets. In some of the most energetic TDE candidates, astronomers detected evidence of powerful, tightly collimated jets of material being blasted away from the black hole at over 99% the speed of light. These relativistic outflows are the most powerful accelerators known in the universe. They are celestial blowtorches capable of punching clear through the host galaxy, but they were only seen in a small fraction of events. Most TDEs seemed to produce no jet at all. Why? What was the crucial difference? Was it the mass of the black hole? Did only the most massive black holes launch jets? Or perhaps it was the black hole's spin. A rapidly spinning black hole, a gravitational gyroscope whipping spacetime around it, might provide the necessary architecture to magnetically channel and accelerate a jet. A stationary black hole, on the other hand, might only be able to pull matter in, not blast it out. Without the ability to get a closer look to probe the environment in the immediate vicinity of the event horizon, we had no way of knowing. The question of what powers these jets and why they are so rare became one of the most significant unsolved problems in high-energy astrophysics. The questions piled up, each one born from the ambiguity of the data. What about the star itself? Did a low-mass star like our Sun get torn apart differently than a massive blue giant? The simulations suggested yes, but the observations were too crude to tell. And what happened to the half of the star that wasn't captured? Physics dictated that roughly half the star's mass would be flung away on unbound trajectories, cast out into the galaxy as a spray of stellar guts. This cloud of debris should be visible, glowing in different wavelengths of light, but searches for this telltale outflow came up empty. Was our understanding of the dynamics wrong, or were our telescopes simply not sensitive enough to pick up this faint, expanding ghost of a star? Every tantalizing signal was a double-edged sword. It brought with it the exhilarating possibility of confirmation, but it also highlighted the profound chasm between our theories and our observational capabilities. We were like 19th century biologists studying the deep ocean by dragging a crude net along the seafloor. We would occasionally pull up a strange unknown creature, proof of a vibrant ecosystem thriving in the abyss. But we could not see how it swam, how it hunted, how it lived in its natural environment. We had the specimen, but the world it came from remained a mystery. The smudges of light from these distant galactic nuclei were our strange creatures from the deep. They proved that black holes were not just passive sinkholes, but active dynamic predators shaping their environments. They hinted at a universe of extreme physics we were only beginning to glimpse, but a hint was not enough. Science demands more than shadows on a cave wall. To truly witness the cataclysm, to move beyond inference and into the realm of direct observation, we needed more than just a brighter flash. We needed to dissect that light to see the event unfold not as a single point, but as a dynamic evolving structure with shape, temperature, and velocity. We needed to pull the event from a featureless smudge of data into a high-definition masterpiece of gravitational destruction. To do that, we would need new eyes on the cosmos, eyes with a clarity, a speed, and a breadth of vision our predecessors could only have dreamed of. The curtain, after decades of watching shadows, was finally about to rise. For generations, our search for these cosmic phantoms was a story of frustration. It was a hunt defined by tantalizingly brief glimpses and blurry after-images. We were like detectives arriving at a crime scene days too late, finding only the faintest outlines of a struggle, the cold echoes of a titanic scream that had long since faded. The universe, in its breathtaking vastness, is also maddeningly fleeting. A star's final violent moments unfold over mere months, a flicker in the lifespan of a galaxy, and our telescopes, powerful as they were almost always looking the wrong way. We were fishing in an infinite ocean, with a tiny net, hoping a monster from the deep would happen to swim into it. The theories were elegant, the simulations beautiful in their brutal logic, but the proof, the hard, undeniable, high-resolution proof, remained elusive. We needed more than a bigger net. We needed to survey the entire ocean all at once every single night. We needed a paradigm shift, a new kind of eye on the sky. And in the silent, high-altitude dark of the Chilean Andes, it was being built. It wasn't a single monolithic giant in the traditional sense like the great reflector telescopes of the 20th century. Instead, this was something different, a new philosophy of seeing. Imagine not one eye, but a compound eye like that of an insect, a mosaic of detectors fused into a single cohesive vision, a digital retina of unprecedented scale. Its mission was not to stare, but to scan, to drink the entire visible sky from horizon to horizon every 72 hours. This relentless, sweeping gaze was made possible by a camera that bordered on the absurd 3 billion pixel Leviathan, the largest digital sensor ever constructed for astronomy. Cooled to a cryogenic whisper of -100 degrees Celsius to suppress the thermal noise that could mask a faint, distant truth, this camera was designed for one purpose: to capture change. Every night as the Earth spun on its axis, the observatory would perform its silent ballet. The dome would slide open, exposing the machinery to the pristine thin air. The telescope, a marvel of optomechanics, would begin its methodical sweep, taking snapshot after snapshot of the celestial sphere. Each exposure, a mere 30 seconds long, would capture a patch of sky 40 times the size of the full moon. And in that brief instant it would gather light that had travelled for millions, sometimes billions of years to reach us. The torrent of information that flowed from this instrument was almost inconceivable. Each night it generated more data than the Hubble Space Telescope has collected in its entire 3-decade history. This was not a stream, it was a deluge, a fire hose of the cosmos spraying petabytes of raw imagery into the observatory's servers. No human, no army of astronomers could possibly sift through such an avalanche. To find one dying star amid a billion steady ones, a billion blinking asteroids and a billion other transient flickers was a task beyond human endurance. The challenge was no longer about seeing, it was about noticing, and for that we turned to a new kind of partner. Deep within the observatory's humming server rooms, a silent consciousness was at work. It was an intelligence forged from silicon and logic, a discovery engine built from millions of lines of sophisticated code. This artificial intelligence had been trained for years on simulated data, on every known type of cosmic variable, the gentle pulse of a Cepheid, the chaotic flare of a red dwarf, the predictable dimming of an eclipsing binary. It had learned the normal rhythm of the sky, the celestial heartbeat. Its sole purpose was to find the anomaly, the arrhythmia. Every new image was instantly compared to a master reference map of the sky, a digital ghost of what that patch of space looked like just nights before. The software would perform a sublime act of cosmic subtraction, erasing the static, unchanging universe, the steady stars, the ancient galaxies, leaving behind only what was new, what had changed, what had just been born or died. Most of these transient alerts were mundane. A satellite glinting in the sun, a previously unknown asteroid, the subtle brightening of a familiar variable star. The AI would classify and dismiss tens of thousands of these every hour. But it was hunting for a very specific signature, a point of light appearing from nowhere in the dead centre of a galaxy that had been silent and dormant for eons. It was looking for the fingerprint of a star being torn asunder. And then on a Tuesday evening it found one. There was no fanfare, no blaring alarm. Just a single line of code and alert flagged with a 98.7% probability score. Designation a 2029 NUJ. To the machine, it was just a string of coordinates, a brightness measurement and a statistical probability. But for us, it was everything. The alert was instantly relayed across the globe to a team of astronomers on call for exactly this moment. On a laptop screen thousands of miles away, the first image appeared. It was unassuming, almost disappointingly so. A field of countless stars, and in the middle a faint fuzzy smudge, a distant galaxy unremarkable among billions of its kind. But a tiny arrow generated by the Discovery engine pointed to a single bright pixel near the galaxy's core that simply hadn't been there 3 nights earlier. The ghost in the machine had found a signal. Now the human element, the crucial layer of intuition and experience, took over. The team worked with frantic, practiced urgency. Was it a supernova? They cross-referenced the galaxy's known properties. It was an old red and dead galaxy, a type that had long since exhausted the fuel needed to create the massive short-lived stars that go supernova. That possibility was unlikely. Could it be an active galactic nucleus, the flickering accretion disk of a supermassive black hole that was already feeding archival data, showed the galaxy's core had been completely quiescent for decades? This light was new. It was sudden. It was violent. The colour of the light was the final critical clue. The initial photometry showed it was intensely, searingly blue, hotter than any normal star. This was the telltale sign of a thermal shockwave of gas heated to millions of degrees, consistent with the models of stellar material being violently compressed and shredded. The team had seen enough. The trigger was pulled. An electronic command, a target of opportunity request, shot out across the world's astronomical networks. This was the moment the new era of astronomy truly began. It initiated a celestial fire brigade, a rapid response system of observatories designed to work in concert. On mountaintops from Hawaii to La Palma, robotic telescopes halted their own surveys, and like obedient sentinels slewed their heavy mirrors across the sky, pointing toward the designated coordinates. High above the atmosphere, orbiting observatories did the same. The Neil Gehrels Swift Observatory, a master hunter of gamma-ray bursts, reoriented its sensitive X-ray and ultraviolet telescopes. Hubble, the venerable icon, shifted its gaze, preparing to bring its legendary resolving power to bear on this single unassuming spot, and the Very Large Telescope with its 4 colossal 8. 2-meter mirrors began to prepare its spectrographs instruments, designed not just to see the light, but to dissect it, to spread it into a rainbow of information. The entire might of modern observational astronomy was now focused on a single point of light, a silent, unfolding catastrophe hundreds of millions of light-years away. What came back to us in the hours and days that followed was beyond anything we had dared to hope for. It was not a blurry smudge or an ambiguous graph. It was a story, the star's final testament written in photons and delivered across the void. For the first time, we witnessed the event not as a single fading point of light, but as a structured, evolving phenomenon. We were seeing the light echo. Think of it not as a reflection, but as a 3-dimensional autopsy report unfolding in slow motion. As the star was ripped apart, it didn't just release a single flash. It created an expanding cloud of incandescent gas, a chaotic shell of its own remains. The light from different parts of this explosion reached us at slightly different times, allowing us to reconstruct the geometry of the cataclysm. The first photons to arrive were the high-energy X-rays, the shriek from the innermost, hottest regions, where the star's matter first slammed into the black hole's embryonic accretion disk. Swift saw this perfectly, a brilliant, sharp spike of radiation the moment of impact, followed by a gradual trembling decline. Then came the ultraviolet light, a wave of energy from the slightly cooler, more extended envelope of gas, the initial shock wave propagating through the shredded stellar atmosphere. Hubble captured this phase with breathtaking clarity, resolving the flare from the background starlight of the host galaxy, giving us a pure, uncontaminated view of the blast. But the most revolutionary data came from the ground-based spectrographs. These instruments acted as cosmic prisms, breaking the incoming light down into its constituent wavelengths, its fundamental frequencies. What they revealed was a symphony of cosmic destruction. The spectrum was initially a smooth, featureless curve of brilliant blue light, the signature of a plasma heated to an impossible temperature. But as the days went by, features began to emerge from this continuum. We saw broad, smeared lines of hydrogen and helium, the star's primary components. The immense width of these spectral lines was a direct measurement of the speed of the ejected gas, a signature of the Doppler effect in action. Some of the gas was flying towards us at nearly 10%. The speed of light, its light shifted towards the blue end of the spectrum. Other parts were rocketing away from us, their light stretched or redshifted. For the very first time, we weren't just guessing at the shape of the explosion, we were mapping it. We could see the geometry of the stellar debris forming not a perfect sphere as some simpler models predicted, but a flattened oblong and wildly turbulent cloud. We were watching the birth of an accretion disk in real time. Then something even more profound appeared in the data. Faint, then stronger spectral lines of heavier elements began to show themselves. Nitrogen, carbon, oxygen. These were the elements forged in the star's core over billions of years of stable life. Now, freed from their gravitational prison, they were broadcasting their presence, their unique atomic barcodes imprinted on the light escaping the chaos. It was an elemental roll call from a dismembered world. We were watching the chemical guts of a sun-like star being spilled across space, a visceral, unambiguous confirmation of what the theories had predicted. The data was so clear, so rich with detail, it felt less like an observation and more like a conversation with the event itself. Every photon carried a piece of the puzzle. The subtle polarization of the light told us about the magnetic fields being stretched and amplified in the swirling plasma. The gentle, days-long flicker in the light curve hinted at the recollision of streams of gas celestial shockwaves echoing within the larger explosion. This was not a blurry photograph of a distant tragedy. This was a high-fidelity recording. The sterile alert from a computer algorithm had transformed into the most detailed chronicle of a star's death ever assembled. The long night of speculation was over. The era of chasing ghosts and interpreting shadows had come to an end. We had finally arrived at the scene not after the fact, but in the very midst of the event. And now, with the star's last words streaming into our telescopes, we could begin the real work of interrogation. Because this spectacular death was more than just a cosmic light show. It was a tool. A celestial probe sent by chance into the most warped and mysterious environment in the universe, and its light now decoded carried secrets not only of the star that died, but of the monster that had killed it. For the first few hours it was pure celebration. The data streamed down terabyte by terabyte, painting a picture of cosmic violence, with a clarity we had only ever dreamed of. On screens around the world, teams of astrophysicists watched a star die, not as a single fluctuating point of light, but as a dynamic, sprawling, luminous entity. This was the moment they had worked towards for decades, the culmination of engineering and theory. It was their digital Sistine Chapel, a masterpiece painted by gravity itself. They had their 8K footage. The initial analysis confirmed the broad strokes of theory, a triumphant validation of human intellect, reaching across millions of light years. They saw the star stretched and distorted, its glowing plasma pulled into a delicate incandescent noodle. They saw the brilliant flare as its constituent atoms were flash-heated to millions of degrees, a death scream written in X-rays and ultraviolet light. The models for a brief glorious moment held true. But then, as the initial euphoria subsided and the hard, meticulous work of detailed analysis began, a disquieting murmur rippled through the global collaboration. A question mark appeared on a monitor in Germany. An anomaly was flagged by a graduate student in Chile. A frantic email filled with confusing spectral charts was sent from a facility in Japan. The beautiful, clean picture they had anticipated, the elegant confirmation of their equations, began to fray at the edges. It started to dissolve into a chaotic, bewildering, and infinitely more fascinating mess. The universe, it seemed, was not content to simply follow our script. The first profound shock came from the jet. Our theories had prepared us for a spectacular display, a focused, coherent beam of particles and radiation, a celestial blowtorch fired from the black hole's pole. This jet, we believed, was the engine's exhaust born from the twisted magnetic field lines as the black hole's immense rotational energy was tapped. It was expected to be a pillar of light, a testament to the awesome power of a spinning singularity. What we saw instead was a monster unbound by our expectations. Instead of a single stable column, the data revealed a wavering, almost drunken plume of energy. It flickered, it sputtered. At times it nearly extinguished itself, only to roar back to life with renewed fury, punching through the swirling debris of the murdered star. But its most baffling characteristic was its motion. It wasn't simply pointing away from the black hole, it was whipping around like a fire hose dropped on the ground. This was not the steady, unwavering lighthouse beam of a pulsar or the stately jet of a mature quasar. This was something wild, untamed, and fundamentally unstable. The phenomenon known as precession is like the slow wobble of a dying, spinning top. But the speed and violence of this wobble were orders of magnitude beyond anything our models had predicted for a tidal disruption event. What could possibly be forcing this billion-ton-per-second particle cannon to thrash about with such abandon? The implication was staggering, and it pointed directly to the black hole itself. The jet is a product of the black hole's spin anchored to its axis of rotation. For the jet to be wobbling so violently, it meant the black hole's own rotational axis, its own internal gravitational gyroscope, was being torqued by an immense force. The leading suspect was the accretion disk, the flattened, swirling whirlpool of stellar gas that was now feeding the monster. The thinking went that if the star came in at a tilted angle relative to the black hole's equator, the disk it formed would also be tilted. This misaligned disk, possessing its own colossal angular momentum, would then exert a gravitational pull on the black hole itself. It was a cosmic wrestling match. The immense but comparatively lightweight disk of stellar gas was physically twisting the spacetime fabric of the 4 million solar mass black hole. The theory known as the lens-thirring effect predicted this could happen, but our footage showed it occurring on a timescale, and with a ferocity that defied belief. We were watching in real time as the final meal of a star literally changed the fundamental orientation of its killer. It was a discovery that sent theorists scrambling back to their whiteboards. How could a disk of mere stellar matter exert such a profound influence on a supermassive object? Did this mean black holes are far more susceptible to their immediate environments than we ever knew? And what did this chaotic, precessing jet do to the surrounding space? Was it sterilizing vast swathes of the host galaxy in a sweeping, unpredictable pattern? Or was it depositing energy and heavy elements in strange, unexpected pockets? The first great revelation from our perfect data was that we had profoundly underestimated the sheer brutal mechanics of this celestial dance. The clean physics of our textbooks had been replaced by the gritty, complicated reality of a gravitational bar fight. As our eyes adjusted to the jet's wild behaviour, we turned our attention to its source, the accretion disk itself. Here too, our expectations of cosmic elegance were shattered. Computer simulations run for years in anticipation of this event had painted a picture of a relatively orderly if turbulent structure. We envisioned a luminous spiral, a celestial pinwheel of gas flowing smoothly inward, getting hotter and brighter as it approached the event horizon. It would be a place of extreme physics, certainly, but it would possess a discernible structure, a pattern we could decipher. The reality we downloaded was a maelstrom. It was not a smooth, symmetrical disk. It was a lumpy, clumpy, violent tempest, a churning sea of plasma racked by shocks and instabilities, on a scale we had never imagined. Instead of a steady inward spiral, the gas appeared to be falling in waves, creating vast transient traffic jams. We could see immense shock fronts brighter and hotter than the rest of the disk, propagating outwards against the inward flow like ripples from a stone thrown into a river flowing the wrong way. These were colossal walls of compressed superheated gas where particles were being slammed together with such force that they radiated energy with the intensity of 1 trillion suns. What was causing them? Were they echoes of the star's initial dismemberment still bouncing around the system? Or were they a new phenomenon, a feature of accretion physics we had never before had the resolution to see. The disk didn't just have waves, it had texture. It was riddled with swirling vortices and eddies, some as large as our own solar system. These were gravitational whirlpools within the larger whirlpool regions, where the gas was temporarily trapped spinning furiously before being violently reincorporated into the main flow. The magnetic fields, which are meant to provide a kind of friction that allows the gas to lose energy and fall inward, were not behaving. Instead of a somewhat orderly web, the footage suggested a tangled, chaotic mess. We saw evidence of magnetic reconnection events, localized explosions where field lines snapped and reconfigured, unleashing colossal flares of energy that flashed across the disk's surface. These were like solar flares, but magnified 1 billion-fold, each one powerful enough to vaporize a planet. It became clear that our simple fluid dynamics models were utterly insufficient. This was not a fluid. It was a magnetized plasma behaving under physical conditions so extreme they cannot be replicated in any laboratory on Earth. The sheer complexity was overwhelming. We weren't looking at a simple drain. We were looking at a cosmic hurricane, a thunderstorm, and a volcanic eruption all happening at once in a space governed by warped spacetime. The questions multiplied with every frame of data. How do these structures form and dissipate so quickly? How do they affect the overall rate at which the black hole is feeding? Is this chaos the normal state of affairs for accretion, or is this a special madness induced by the sudden violent arrival of an entire star? We had hoped the disk would be a Rosetta Stone for understanding black hole accretion. Instead, it was a library of books written in a language we had yet to even recognize, let alone translate. And then there was the ghost. In any tidal disruption event, not all of the star is consumed. Depending on the trajectory of its final fatal approach, a significant fraction of the star's mass can miss the black hole entirely. It gets flung away on a long looping path, a surviving remnant destined to wander interstellar space as a strange tidally unbound stream of gas. Our models predicted a clean getaway for this stellar ghost. We expected to see a long faint tail of material stretching away from the bright chaos of the accretion disk, a clear line between the consumed and the escaped. But the ghost of star assassin 21QJ hadn't escaped. Not yet. Our new impossibly sharp view revealed something far more poignant and gravitationally complex. A thick luminous streamer of gas, clearly identifiable as the star's outer layers, had indeed been ejected just as predicted. But instead of flying off into the void, its trajectory was bending. It was being pulled back. We watched mesmerized as this stellar remnant, a vast ribbon of hydrogen and helium that still retained the memory of being a sun, performed a slow, graceful and ultimately doomed U-turn in space. It was caught in a gravitational ballet with the very monster that had destroyed it. It was now on a long elliptical orbit, a lonely satellite of its own demise. This discovery opened up an entirely new dimension to the event. The feeding wasn't over. It wasn't a single cataclysmic meal. It was a banquet with multiple courses. This returning stream of gas would on its next pass inevitably interact with the turbulent accretion disk already in place. It would rain down upon it, injecting fresh material and momentum, potentially triggering a whole new round of flares and instabilities. We were going to witness a collision between the star's past and its present. The data forced us to ask, is this a common feature of these events? Do black holes play with their food? Does this recurring partial disruption change how the black hole grows over cosmic time? This orbiting remnant became a gravitational probe of exquisite sensitivity. By tracking its precise path, we could map the gravitational field around the black hole with unprecedented accuracy, testing the limits of Einstein's general relativity in this strong field regime. But it was also a profoundly sad sight. You could not help but anthropomorphize it. You saw a sun that had been ripped apart, with half of it being consumed in a blaze of glory, while the other half was forced to circle the scene of the crime, a perpetual silent witness bound by the inescapable chains of gravity. It was a haunting confirmation that in space even the ghost cannot escape the pull of the abyss. This single unexpected detail transformed our understanding from a simple smash and grab to a long drawn-out and deeply complex cosmic tragedy. Finally, As we looked beyond the immediate carnage, a new riddle emerged from the darkness. The initial flash of the star's disruption was so incredibly bright that it acted like a cosmic flashbulb illuminating the black hole's surrounding environment. As this light travelled outwards, it would reflect off any clouds of dust and gas that might be orbiting further out. These reflections, or light echoes, arrive at our telescopes later than the initial flare, their delay telling us exactly how far the reflecting clouds are from the central engine. It's a way of performing a CT scan on the black hole's neighbourhood. In the past, with less sensitive instruments, we had only caught fleeting glimpses of these echoes. But now with our 8K view, we could see the echoes resolve into intricate, beautiful and deeply perplexing patterns. We saw arcs, rings and filaments of light appear and fade, painting a ghostly picture of the material hidden in the dark. The problem was the picture they painted made no sense. The echoes revealed a complex, clumpy distribution of dust in planes that were completely misaligned with both the accretion disk and the black hole's spin axis. It was a third independent axis of rotation in the system, a ghost in the machine that we had no theory to account for. Where did this dust come from? Was it the shattered remains of a previous victim, another star, or perhaps a giant planet that had met its end centuries ago, its dusty corpse still orbiting in a silent graveyard? Or was it material that had been captured from the galaxy itself, slowly settling into a stable but tilted orbit over millions of years? Each possibility carried profound implications. If it was the debris of past meals, then these tidal disruptions are not clean, isolated events. They leave behind a complex, polluted environment that affects every subsequent event. The black hole's dining room was filled with the crumbs of its previous feasts. If it was captured galactic material, it meant we had a new way to probe the mysterious processes by which supermassive black holes gather fuel from their host galaxies, a process fundamental to understanding how they co-evolve. The intricate dance of these light echoes became the ultimate puzzle. We were using the light from one shredded star to illuminate the fossilized remnants of another, all while a black hole, an accretion disk and a surviving stellar stream were performing three different uncoordinated ballets in the center. The initial question, what does it look like when a black hole eats a star, had been answered, but in its place a dozen more, deeper and more fundamental, had bloomed. We had opened a door expecting to find a room, but instead we found a hallway that branched into 1,000 other corridors, each one leading deeper into the mystery. The era of simple models was over. The age of cosmic complexity had just begun, and then after months of computational fury, the pieces finally lock into place. Across a global network of supercomputers, trillions of calculations converge, weaving every disparate thread of data into a single coherent tapestry of cosmic violence. The faint radio whispers, the searing X-ray signatures, the subtle shifts in visible light, and now the breathtaking high-fidelity frames from our 8K observatory. All of it is finally synthesized. What emerges from this digital crucible is not merely an animation, not an artist's impression, but a ghost resurrected. This is the star's final memory played back for us, in excruciating, unprecedented detail, a four-dimensional reconstruction anchored frame by frame to observed reality. Before us, the abstract numbers and spectral lines melt away, replaced by the most accurate portrayal of a star's death humanity has ever constructed. We are no longer just observing a distant cataclysm, we are bearing witness. The journey into the heart of the maelstrom begins not with a bang, but with a fatal gravitational misstep. Long before its final fiery moments, the star was an unassuming traveller, a brilliant sphere of hydrogen and helium, burning with the quiet dignity of its kind for millions of years. It traced a lazy elliptical path through the galactic centre, a celestial ship of light on a voyage it had completed thousands of times before. In the preceding acts of its life, its orbit had always kept it at a respectful distance from the central darkness, the slumbering supermassive black hole that governs this stellar metropolis. But the cosmos is a place of subtle, relentless nudges. A close pass with another star, a slight gravitational jostle from a dense cluster. The precise cause is lost to time, but the consequence was a minute, almost imperceptible alteration of its trajectory. Its orbit tightened. Its path began to curve ever so slightly inward, a course correction that sealed its doom 1,000 years before we would ever see its light. Now as our simulation begins, we watch it make its final approach. It glides through the void, still whole, still luminous, utterly oblivious to the precipice it is about to cross. You're there on its surface, a place of unimaginable temperatures and pressures where plasma churns in convective currents, larger than our own world. From this vantage point, the black hole is not yet a monster. It is simply a point of impossible blackness, a perfect circle of nothing hung against the dense tapestry of the galactic core. Yet you would feel its presence not with your eyes, but in your very bones. A strange and subtle force would begin to pull at you, a phantom tide with no ocean to move. This is the beginning of the end. This is the influence of the tidal force, the weapon a black hole wields. It is gravity's gradient made manifest, a force that grows so steeply, so exponentially, that it begins to exert a different pull on every part of the star's body. The side of the star facing the black hole, the leading edge of this doomed world, is being tugged with monumentally greater force than the side facing away. The difference is infinitesimal at first, a whisper of a strain across a body hundreds of thousands of miles in diameter. But the star is now accelerating, plunging deeper into the gravitational well, and that whisper is about to become a scream that will tear it apart from the inside out. The star's spherical integrity, the perfect balance between its own gravity pulling inward and the outward pressure of its nuclear furnace, begins to fail. We see it in the 8K reconstruction with horrifying clarity. It begins to distort its perfect circular profile, elongating into an egg shape, a celestial body being stretched on a gravitational rack. The star is fighting for its life. Its internal fusion rate may even spike as its core is compressed, a desperate final surge of energy against the inevitable. But no amount of internal power can fight this. The external tidal force is now overwhelming the star's own self-gravity, the very force that has held it together for eons. The stretching accelerates catastrophically. The egg becomes a teardrop. The teardrop becomes a spindle. The stellar material, no longer bound by its own gravitational field, starts to peel away. Imagine pulling a single thread from a ball of yarn. Now imagine that thread is a river of plasma heated to millions of degrees, and the ball of yarn is a world 100 times more massive than our Earth. This is the moment of tidal disruption. This is spaghettification, a term that sounds almost whimsical, but describes a process of utter annihilation. The star is being unspooled. Its coherent structure, its identity as a star, ceases to exist. It is no longer a singular object, but is violently and irrevocably disarticulated into a colossal stream of its own constituent matter. Our visualization, meticulously built from the light curves and spectral data, shows this process in agonizing slow motion. We see the outer layers of hydrogen and helium stripped away first, shredding into luminous filaments that trace the magnetic field lines. Then the deeper, denser layers are exhumed, pulled from the failing core like ribbons of fire. The star doesn't explode in the traditional sense of a supernova. It is systematically and brutally unraveled, its mass drawn out into a luminous noodle of plasma that is thousands of times longer than it is wide. It is a river of stellar fire, one end still anchored to the star's dissolving core, the other end already accelerating towards the event horizon at a significant fraction of the speed of light. The destiny of this stellar river is now twofold, dictated by the cold, unforgiving laws of orbital mechanics. Not all of the star will be consumed. The data reveals a clear bifurcation. Roughly half of the star's mass, the part that was on the outer edge of the original orbit, is on a trajectory that carries it away from the black hole. This material is given such a powerful gravitational kick that it is flung out into interstellar space at immense speed. In our reconstruction, we see this unbound stream arc away, a ghostly tendril of fading light, a cosmic epitaph travelling through the galaxy. These are the so-called hypervelocity stars, and for the first time we are witnessing the exact mechanism of their birth, seeing the precise physics that can launch a sun-sized object out of its home galaxy. This stream will travel for millions of years, a diffuse cooling cloud of gas that carries the chemical signature of the world it once was a ghost of a star haunting the intergalactic void. Its story is one of escape, a testament to the sheer propulsive power of this encounter. But for the other half of the star there is no escape. This is the matter on a bound trajectory, the material whose momentum was not enough to overcome the black hole's grasp. This is the part of the stream that turns back, pulled by the immense gravity into a descending spiral. It is this material that will power the celestial fireworks we have travelled so far to understand. It does not fall straight in. To do so would violate one of the most fundamental laws of the universe, the conservation of angular momentum. Just as a figure skater spins faster when they pull their arms, in this falling river of gas must spin faster and faster as it gets closer to the black hole. The stream collides with itself, its leading edge catching up to its tail as it completes its first terrifying orbit. The collision point is a place of apocalyptic violence. Shockwaves brighter than 1,000 suns erupt through the gas, compressing and superheating it to temperatures we normally only see in the heart of a nuclear explosion. And from this chaos, a new temporary structure is born, the accretion disk. This is the luminous vortex of stolen light, the central engine of the entire event. It is a swirling incandescent platter of what was once a star, a cosmic grindstone where matter is pulverized and converted into pure energy with terrifying efficiency. The 8K data gives us an unprecedented view into the disk's structure. It is not a smooth, serene whirlpool. It is a roiling, turbulent tempest. We can see hotspots regions where magnetic field lines have become tangled, snapping and reconnecting in explosions that launch flares of X-rays. We can see density waves spiraling inward traffic jams in the flow of gas that glow with ferocious intensity. The friction within this disk is unimaginable. Particles of gas moving at nearly the speed of light rub against each other, generating so much heat that the disk begins to shine with a brilliance that temporarily outshone every other star in its galaxy combined. This is the source of the incredible flare of light our telescopes first detected, the death scream of the star translated into a beacon visible across 250 million light-years. We are watching matter being heated to its absolute limits, stripped down to a soup of bare nuclei and electrons glowing fiercely in X-ray and ultraviolet light before it takes its final plunge. The colour and temperature of the light from this disk, captured in our spectra, act as a celestial thermometer. From it we can deduce the speed of the infalling gas, the density of the disk, and even the spin of the black hole itself. A spinning black hole, we have theorised, twists space-time around it, like a vortex, a phenomenon known as frame dragging. This should alter the shape and stability of the innermost edge of the accretion disk. And in the data for the first time with this level of clarity, we see the telltale signature, a warping and wobbling of the disk's inner ring, a gravitational gyroscope confirming that this behemoth is not static, but spinning at a significant fraction of its theoretical maximum. The star is not just feeding a black hole, it is feeding a spinning, space-time bending vortex of colossal power. The climax of the consumption is a relentless, sustained downpour. The accretion disk is not a permanent structure. It is a transient holding pattern, a cosmic waiting room for oblivion. Continuously a stream of superheated plasma from its inner edge breaks away and crosses the final threshold, the event horizon. This is the point of no return, the one-way membrane from which nothing, not even light, can escape. As the matter falls across this boundary, it releases one final titanic burst of energy. This is not light from inside the black hole, which is impossible. It is the light from the matter at the very moment of its crossing, a final flare of gravitational potential energy being converted into radiation. It's like a waterfall. The water itself is silent, but the roar comes from the water crashing at the bottom. Here the roar is a blinding torrent of high-energy X-rays and gamma rays, the last possible signal the universe can receive from this doomed material. This is the flickering chaotic light curve our telescopes recorded for months. And now we understand its source. We are watching the black hole's inconsistent, messy feeding process, a cosmic banquet characterized by gulps and belches of radiation. In some more extreme cases of these events, the process doesn't end there. The intense magnetic fields anchored in the accretion disk, twisted into tight coils by the black hole's spin, can act like a cosmic particle accelerator. They can capture a small fraction of the infalling matter, and instead of allowing it to fall in, accelerate it outwards in two oppositely directed, tightly focused beams. These are relativistic jets, celestial blowtorches that travel at over 99% the speed of light. Our radio telescopes scoured this event for such a jet, and while only a faint outflow was detected, our model, now calibrated with this incredible data, can show us what could have been. With a slight change in the black hole's spin or the star's initial trajectory, this event could have produced a jet powerful enough to punch a hole clear through its host galaxy, a beam of energy that could sterilize any planet in its path for thousands of light years. It is a sobering reminder that as beautiful as this destruction is, it represents a concentration of power that defies all terrestrial comparison. So this is it. The mystery is solved. The question of how. A star is devoured, a process we have only ever glimpsed in blurry snapshots, and theoretical models is now laid bare. We have the complete narrative, a continuous story from the first gravitational tug to the final photon emission. We watched a world get stretched into a filament, we saw that filament bifurcate into an escapee and a captive, and we witnessed the captive spiral inward to form a temporary blazing corona around its executioner. We have mapped the turbulence, measured the temperature, and confirmed the spin of the abyss itself. The raw power is undeniable, a force that can disassemble a sun with the casual indifference of an ocean tide eroding a grain of sand. Yet in this process there is a strange and profound beauty. The universe in its most violent acts creates moments of the most intense and fleeting brilliance. The star in its death became more luminous and more magnificent than it ever was in its long quiet life. The feast is over. Feast is. The brightest phase of the accretion disk has faded as the last of the bound stellar material is consumed. The X-ray glare subsides, and the black hole returns to its quiescent invisible state. But the echoes of this cosmic banquet will reverberate for millennia, carrying secrets we are only now beginning to decipher. The hypervelocity stream of escaped gas will travel the void, a messenger from a world that no longer exists. The light and radiation from the flare even now continue their journey across the cosmos, carrying the detailed story of this destruction to any civilization advanced enough to read it. We have captured a chapter of that story, and it has transformed our understanding, but it has also opened the door to deeper questions. How often does this happen? What role does this stellar shredding play in the growth of supermassive black holes, and by extension in the evolution of the galaxies they inhabit? The death of this one star has illuminated the darkness for us, but it has also shown us just how much more darkness there is left to explore, and so the celestial scream fades into the cold, silent depths of intergalactic space. The final brilliant flare, a star's death cry, broadcast across millions of light years, now dwindles into a ghostly afterglow. What you have just witnessed in detail, more visceral and immediate than we ever thought possible, was not merely an act of cosmic violence, it was a revelation. It was the moment a persistent, elegant theory sketched out in chalk on university blackboards and modelled in the ghost realm of supercomputers finally materialised into raw, terrifying and profoundly beautiful reality. The ephemeral light from that doomed sun, now captured and stored on our servers, has become a veritable Rosetta Stone for understanding the universe's most enigmatic monsters. For decades we spoke of spaghettification with a hint of scientific poetry, a clean, almost cartoonish analogy for an impossibly violent process. We imagined a star stretched like cosmic taffy by the tidal forces of a black hole, an elegant unspooling of stellar matter into the void. But the data flowing from this event, the information encoded in every single photon of that dying light, tells a far more intricate and chaotic story. It grants us the power to move beyond analogy and conduct a cosmic autopsy. We can see now with chilling precision how the star did not simply stretch. It was pulverized by gravitational shear. The side of the star closer to the black hole was pulled with so much more ferocity than the far side that the star's own gravity, the very force that had held it together for billions of years, became utterly irrelevant in its final moments. It was a battle between two titans of gravity, and the star never stood chance. Within the spectral signatures of the swirling debris we read, the star's internal chemistry laid bare its layers of hydrogen, helium, and heavier elements separated and sorted by the black hole's immense power. We can measure the temperature gradients across the filament of stellar gas, seeing how frictional forces heated it to millions of degrees even before it properly fell into the maelstrom of the accretion disk. This is physics at its most extreme, a domain previously inaccessible to direct observation. We can discern the star's original trajectory, its angle of approach, and calculate how these initial conditions dictated the exact shape and duration of its demise. A slightly different angle, a bit more velocity, and it might have been flung away scarred but intact. A more direct path, and it would have been swallowed whole, leaving barely a ripple. But this star, its fate sealed eons ago by its random walk through the galactic core, threaded the needle of cosmic annihilation perfectly. It passed just inside the tidal disruption radius, the gravitational point of no return, ensuring its destruction would be both complete and spectacularly visible. The light curve, the graph of the event's brightness over time, became a detailed script of the murder. Its initial sharp rise told us of the moment the star's outer layers were first torn away, a process called shock breakout, where the compressed stellar core was violently exposed. The long, steady decline that followed was not the signature of a simple cooling ember, but the complex chronicle of stellar material raining back down onto the black hole over months and years, a slow, agonizing process of being consumed. Far from a simple, smooth funnel of matter, the nascent accretion disk you saw form was a turbulent, lumpy, chaotic whirlpool. We witnessed hotspots flaring up and dying down, temporary knots of magnetism and superheated gas that betray the immense complexity of plasma physics in a warped space-time environment. These fluctuations, once just theoretical noise in our models, are now distinct data points. They tell us about the magnetic fields that were once threaded through the star, now amplified and twisted into a cosmic dynamo that powers the entire cataclysm. We're no longer guessing at the forces at play, we are measuring them. We are watching in real time the birth of one of the universe's most luminous objects from the corpse of one of its most common. Every flicker, every colour shift in that swirling disk of doom is a new line in our textbook, a new parameter for our simulations, transforming our abstract understanding into something tangible and concrete. The ghost of that star has illuminated the darkness, and in doing so has taught us more about the fundamental nature of gravity than 1,000 earthbound experiments ever could. The destruction of the star was merely the opening act. The true protagonist of this story, the silent, invisible force at the centre of the whirlpool, has also been forced out of the shadows. Before this event, the supermassive black hole was a ghost in its own galaxy, a dormant monster sleeping between meals. Its presence was inferred only by the subtle dance of the stars orbiting its unseen centre of mass. It was a statistical certainty, a gravitational anchor, but not a living, breathing entity. Now it is awake. In feeding upon the star, the black hole has been reignited, transformed from a passive object into a ferociously active galactic nucleus, a nascent quasar. The energy being unleashed from that pinprick of space-time is staggering, almost beyond human comprehension. The accretion disk, burning at millions of degrees, is now outshining all the billions of other stars in its host galaxy combined. A single object no larger than our solar system is generating more light than a city of 100 billion suns. This is the quintessential power of a black hole, not just as a destroyer, but as the most efficient engine of creation in the cosmos. Nothing in the universe is better at converting mass into pure energy than matter falling into a black hole. As the stellar gas spirals inwards, its orbital energy is violently extracted through friction and magnetic turbulence, and then radiated away as light across the entire electromagnetic spectrum, from radio waves to the most energetic gamma rays. We are capturing this radiation, dissecting it, and using it to weigh the monster. The total luminosity, the sheer power of the broadcast, gives us a direct measure of the rate at which the black hole is feeding. We can estimate that it is consuming several Earth masses worth of stellar material every single second, a feast of cosmic proportions. By tracking the innermost edge of the accretion disk, where the gas makes its final fatal plunge past the event horizon, we can begin to probe the black hole's most fundamental property, its spin. According to Einstein's theories, a black hole is defined by only three things: its mass, its charge, and its spin. For astronomical black holes, the charge is negligible. Mass determines its size, its raw gravitational pull, But spin is where things get truly strange. A spinning black hole, a Kerr black hole, doesn't just curve space-time, it twists it, dragging the very fabric of the universe around with it in a vortex called the ergosphere. This cosmic gyroscope has a profound effect on the matter orbiting it. The light from the gas in the accretion disk is warped and bent by this frame-dragging effect, causing subtle but measurable oscillations in the light we receive. You saw it as a strange, almost liquid wobble in the heart of the maelstrom. For us, that wobble is everything. It is a signature, a fingerprint of the black hole's spin. Analysing it allows us to calculate how fast this behemoth is rotating, which in turn tells us its life story. A fast-spinning black hole is a sign of a violent past, one filled with mergers and chaotic accretion events. A slow-spinning one suggests a more placid history. For the first time, we are not just inferring the existence of a black hole, we are psychoanalyzing it. And then there are the jets. The colossal focused beams of energy you saw erupting from the poles of the black hole are the system's exclamation points. Not all of the star's material is doomed to fall into the abyss. A small fraction caught in the tightly wound magnetic field lines, anchored to the spinning black hole, is instead accelerated to nearly the speed of light and violently ejected back into space. These jets are celestial blowtorches capable of carving vast cavities in their host galaxy's interstellar gas. They act as a form of cosmic feedback, a self-regulation mechanism that can halt star formation, inflate enormous bubbles of hot gas, and fundamentally sculpt the evolution of the entire galaxy. For decades we have seen the ancient fossilized evidence of this process in distant galaxies, but we have never before witnessed the ignition. We have never seen the switch being flipped. This event has provided us with a front-row seat to the birth of a galactic feedback engine, watching as a star's death becomes the catalyst for shaping the destiny of billions of other stars yet to be born. In this one singular cataclysm, we see the entire life cycle of galactic evolution, encapsulated creation, destruction, and rebirth, all driven by the unquenchable hunger of the abyss. This single breathtaking observation is not an end. It is a profound paradigm-shifting beginning. It represents the dawn of a new era in observational astrophysics, an era we might call transient astronomy. We are no longer limited to studying the static, unchanging cosmos. We are now building the tools to watch the universe in real time, to catch it in the act of changing, evolving, and exploding. The success of this observation, the sheer wealth of data harvested from this one star's final moments, serves as a blueprint, a proof of concept for the next generation of cosmic explorers. We now know with absolute certainty what to look for. The specific light signatures, the X-ray flashes, the radio echoes, these are the telltale fingerprints of a tidal disruption event. We have moved from searching for a needle in a cosmic haystack to having a powerful magnet that can pull the needle directly out. The observatories of the near future are being designed with precisely this kind of science in mind. Consider the Vera C. Rubin Observatory, soon to come online in the mountains of Chile. This is not a telescope designed to stare intently at one object for a long time. It is a sentinel, a wide-eyed guardian that will scan the entire visible southern sky every few nights. It will produce a motion picture of the cosmos, cataloguing billions of objects and crucially flagging anything that changes, flickers or flashes. Instead of finding one tidal disruption event every few years by sheer luck, Rubin will likely find hundreds. It will turn these impossibly rare cataclysms into a regular, predictable survey. We will build up a statistical sample, a veritable zoo of stellar deaths. We will see large stars and small stars, young stars and old stars, all meeting their end in the jaws of black holes of different sizes and spins. We will begin to see patterns to understand the demographics of these events and use them to conduct a census of the universe's previously invisible population of dormant supermassive black holes. We will finally be able to map out where these sleeping giants reside, creating a complete atlas of the gravitational hazards lurking in the hearts of galaxies. And we will look with more than just eyes of light. The Laser Interferometer Space, Antenna or LISA, will be a gravitational wave observatory in space, an antenna for the vibrations of spacetime itself. When a star is torn apart by a black hole, it doesn't just scream in light, it screams in gravity. The violent acceleration of stellar matter creates ripples in the fabric of reality gravitational waves that travel outwards at the speed of light. Lisa will be tuned to hear these specific faint whispers from the edge of the abyss. The combination of light-based observatories like Rubin and gravitational wave observatories like Lissa will give us a complete multi-messenger picture of these events. Light tells us about the matter, the temperature, the chemistry, the plasma physics. Gravitational waves will tell us about the gravity to the pure, unadulterated warping of space-time, the intimate details of the black hole's mass, and spin the final, terrifying moments of the plunge. It will be like watching a thunderstorm, not just with our eyes, but with our ears as well, feeling the thunder as well as seeing the lightning. This new wealth of data will transform these cataclysmic events into something more cosmic laboratories. These are environments that we can never hope to replicate on Earth. The gravity is too strong, the temperature's too high, the magnetic field's too intense. Here at the event horizon of a black hole, the laws of physics are pushed to their absolute breaking point. Einstein's theory of general relativity has passed every test we have ever thrown at it, with flying colours, but it has never been tested in a place like this. By precisely tracking the orbits of gas blobs in the accretion disk and timing the arrival of both light and gravitational waves from the disruption, we can interrogate general relativity with unprecedented precision. Does space-time behave exactly as Einstein predicted in this extreme curvature? Are there subtle deviations that could hint at a deeper, more complete theory of quantum gravity? The holy grail of modern physics, a tidal disruption event is a gravitational scalpel, slicing open the fabric of reality for us to peer inside. Ultimately, the journey you have taken with us from a fleeting theoretical concept to the raw visceral footage of a universe in motion is a testament to human curiosity. We are a species defined by our relentless need to understand, to look out into the darkness, and not just see points of light, but to comprehend the story they are telling. Each of these events is a chapter in that grand cosmic narrative. They are violent and destructive, yes, but they are also profoundly illuminating. They are the universe's way of revealing its most guarded secrets. In the dying light of a single unremarkable star, we have found a key that unlocks the nature of gravity, the life cycle of galaxies, and the very structure of space-time itself. The next decade of exploration promises to turn that key. We stand on the precipice, armed with new eyes and new ears, ready to witness a sky filled with these ephemeral lighthouses of destruction. We will use their light to navigate the darkest and most mysterious corners of existence, continuing our unending quest to understand our place within this vast, terrifying, and achingly beautiful cosmos. The show is only just beginning.